Let's talk about the fundamental theorem of calculus. This is an important concept. So, the fundamental theorem of calculus connects differential calculus and integral calculus together, and there are two parts. Part one, the differential part, is if you have a function g of x, which equals the integral from a to x of some function f of t dt, then g prime x is equal to f of x. Part two, the integral part, if you have some function f of x that ranges from a to b, then this equals the limit as n goes to infinity of I equals 1 to n f of xi times delta x, and this is also equal to capital F of b minus capital F of a, where capital F is any antiderivative of f of x. So if this doesn't make sense right now, don't worry. I'm going to walk you through some examples, and you'll be able to understand. So first of all, let's say we have some function g of x is equal to from -4 to x of e to the power of t cos squared 1 minus 5t dt. And let's say we're asked to find what g prime x is equal to. Well, this is easy. G prime x is equal to, just replace the t with the x. That's all you got to do here. It's equal to e to the power of x cos squared 1 minus 5x. Number two, g of x, let's say this time is equal to from 1 to x of t4 plus 1 over t squared plus 1 dt. Okay, well, we want the x on the top where the 1 is. So this is actually equal to negative x1 t4 plus 1 over t squared plus 1 dt. Okay, so this is equal to, now you can just simply plug in x, replace the t with x. So that's x4 plus 1 over x squared plus 1. Let's move on to number 3. Here we have another example from 2 e to the power of x t squared dt. Find h prime x. Sorry, I forgot to mention that this was h of x, but yeah, this is h of x. So h prime x, this one is slightly different. So h prime x, yes, you replace the t with e to the power of x. So this is equal to e to the power of x squared. Replace the t with e to the power of x. But you also need to multiply the derivative of e to the power of x. So times e to the power of x. So this is equal to e to the power of 3x. This concept was a little confusing, so I'm going to make another example related to this. Yeah, so let's just call this g of x. I don't know, I could have just said, yeah, let's just say we want to find g prime x. Well, similar to question number 3, g prime x, let's replace the t with 2x squared. So 2x squared to the power of 4 plus 1 times the derivative of 2x squared, which is 4x. And this is equal to 4x times 16x to the power of 8 plus 1. I have one last question here, and this is a bit of an interesting special question. Let's say f of x was equal to the integral from from 3x squared to sine x e to the power of t minus 1 over t dt. Here's the thing. Both the top and bottom bound are functions of x. And the bottom bound is not some constant like 0, 1, or 2. It's 3x squared. We're not familiar with how to solve integrals of this style, so let's change it into something we know we can solve. This is equal to 0 to sine x e to the t minus 1 over t dt minus from 0 to 3x squared e to the t minus 1 over t dt. And now we can find the derivative of both of these integrals simultaneously. So now f prime x is equal to replace the t with sine x, so e to the power of sine x minus 1 over sine x, and times the derivative of sine x, which is cosine x. Now let's focus on the second integral derivative. So here e to the power of t, e to the power of 3x squared minus 1 over t 3x squared. The derivative of 3x squared is 6x. And you can leave it like this, but if you want to, simplify, that's fine. This is just equal to cotangent x times e to the sine x minus 1 minus 2 over x times e to the power of 3x squared minus 1. So yeah, that's the fundamental theorem of calculus, part 1. Alright, let's move on to the fundamental theorem of calculus, part 2. We have this integral from a to b of f of x dx, which is equal to this odd-looking summation notation, which is equal to capital F of b minus capital F of a, where this capital F is any antiderivative of f of x. So it's basically saying that the definite integral of f of x over the interval f of a to over the interval from a to b is calculating, my spelling is off, is calculating the area underneath f of x. So if you had a function like, say this, let's say x, and this is f of x, and let's say f of x looked something like this, from a to b, like this. The integral from a to b, f of x dx, is equal to this area that I'm shading right here inside, that it's above the x-axis. And this is equal, this is what it equals to. It equals a. I'm going to erase this thing that looks like a negative sign, but that's what the definite integral is calculating. Now, to visualize what's going on here, let's say you had a function f of x. and you're trying to find the area underneath f of x from a to b. The way you can do it, the way you can do it, this thing, lim n goes to infinity, I equals 1, n, f of x, I times f of delta x, is saying you can use infinitely many rectangles to find the area under f of x. That's all it's saying. So if I were to draw something like this, okay, so you have something like this, you can break up, you can draw many rectangles, and the more rectangles you draw underneath this area, the better you can approximate what the actual area under f of x is going to be. Infinitely many rectangles. So the more rectangles you have, the better your estimation will be to what the actual area is underneath f of x. And if you have infinitely many rectangles, you can exact value what the area will be. So let's do an example. Let's evaluate the integral from 0 to 3 of 4 minus x dx. And I'm going to solve this in 3 different ways. Solve this 3 ways. The first way is geometrically. So here 4 and here 4. 3 is right here because we're going from 0 to 3, right? So, and f of 3 is equal to 1. So we want to find this area, this shaded area here, right? That's above the x-axis. Well, this is equal to, you can break this up into a triangle and a rectangle. Zero, 4, y equals 1 at f of 0. So then, and you can also plus a rectangle, 0 to 3, and 1, and 1. So this area A that we're evaluating is equal to the area of this triangle plus this rectangle. And the area of the triangle is just 1 over 2 times 3 times 3. And the area of the rectangle is 3 times 1. When you calculate it out, you'll get the answer of 7.5. So this integral is equal to 7.5. Now, let's evaluate it using the definition of the integral. When you're asked to evaluate an integral like this using the definition of the integral, you want to be able to remember these summation formulas. If you're doing an exam, it's really recommended that you remember these 4 formulas that I've written down below. These are the summation formulas you'll need that are necessary to solve this integral. So I'm going to show you how to solve this integral right here using the definition of the integral. So here, we know we're going to use our formula. So A is equal to lim n goes to infinity. I equals 1 to n f of xi delta x. And here you want to be able to know some formulas. Delta x is equal to b minus a over n. And xi is equal to a plus I times delta x. So yeah, let's get to it. A is equal to lim n goes to infinity summation n f okay, so f of xi, f of, so a equals 0 and b equals 3, so this is 3i over n, and delta x is equal to 3 over n. I'll write this on the side. I should have clarified. So delta x was equal to 3 minus 0 over n, so this is 3 over n, and xi is equal to a equals 0, so it's 3i over n. Yeah. Yeah, so this is equal to, let's continue on, lim n goes to infinity, I equals 1 to n. So f of x is 4 minus x. So we have 4 minus 3i over n times 3 over n. And this is equal to lim n goes to infinity n. Let's just multiply. So this is 12 over n minus 9i over n squared. Let's separate this into two separate summations. A equals lim n goes to infinity. And, okay, so for the 12 over n, we can separate out the n. So it's 1 over n. Okay. I equals 1 to n, just put 12. Minus lim n goes to infinity 9 over n squared times I equals 1 to n, just I. And using our summation formulas right here, this is equal to lim n goes to infinity 1 over n. So if it's just the summation of some constant c, this is equal to cn. So times 12n minus and the summation of I is times right here n times n plus 1 over 2. And now this limit right here, 12n divided by n, is just equal to 12. This limit right here, so you have 9 over 2 times n squared plus n divided by n squared. As n goes to infinity, this rational value is just equal to 1, so it's just minus 9 over 2. which is equal to 12 minus 4.5, that's 7.5, which confirms our answer when we evaluated it geometrically. And now let's use the third way to solve it. Actually, I'm not going to erase the whiteboard. So the third way. Well, the third way, so 0 to 3, 4 minus x dx. Well, let's just find the antiderivative. So then 4x minus 1 over 2x squared from 0 to 3. Capital F of 0 is just 0, so capital F of 3, this is equal to 4 times 3 minus 0.5 times 9. 12 minus 4.5 is equal to 7.5. So in all three methods, we got 7.5. So the area under 4 minus x from 0 to 3 is 7.5. And suppose that the graph of a continuously differentiable function y equals f of x passes through the following points 1, 2, 2, 4, 3, 5, and 5a. Find the value of a given that this formula exists. Okay, so let's find the value. So the integral of f prime of x is just f of x. Don't consider what c is. So here we have the left-hand side right here. We will have f of 2 minus f of 1 is equal to 2 times f of 5 minus f of 3. F of 2 minus f of 1, that's 4 minus 2, is equal to 2 times f of 5 is a, and f of 3 is 5. Alright, so 2 times a minus 5 is equal to 2, and a is equal to 6. Our next example is, given that these three integral values exist, what is the integral from negative 5 to 12 for f of x dx? So here is a tip. Here's a bit of a note that you should remember. The integral of a to b f of x dx is equal to the negative. You can flip a and b. It can also be equal to the integral from b to a of f of x dx negative. So if you want to switch b and a from top to bottom, you need to change the sign from positive to negative. This is an important tip. Okay, so using that tip, here is what we have. Negative 10 to 12. I always like to do this. F of x dx. It's not 6, it's negative 6. Negative 10 to 100. F of x dx is equal to 2. Negative 5 to 100. F of x dx is not 4, it's negative 4. Alright, and now we need to find the integral from negative 5 to 12. First of all, the integral from negative 10 to 100 f of x dx minus the integral from negative 5 to 100 f of x dx will be just the integral from negative 10 to negative 5 f of x dx. And I want you guys to see why this is the case. Let's suppose you have this diagram is not drawn to scale, so don't worry about these values not looking right. Let's say you had some function like this, okay? Your f of x. Let's suppose that negative 10 was here, negative 5 was here, and that 100 was here. So the integral from negative 10 to 100, when you subtract the integral from negative 5 to 100, you're subtracting this integral right here, and all you're left with is the integral from negative 10 to negative 5, like this. So, yeah. That is thus equal to minus negative 4, which is equal to 6. The integral from negative 10 to 12, f of x dx, minus the integral from negative 5 to 12, f of x dx, is equal to the integral from negative 10 to negative 5, f of x dx. And for the similar reason as I just explained, yeah, this is true. So from negative 10 to 12, then that would be equal to negative 6. So negative 6 minus negative 5 to 12, f of x dx is equal to 6, as we found earlier. So then our final answer to this equation, to this integral, is negative 12. That's the answer. The last question I have is, let R be the region bounded by the functions y equals x squared divided by 2 and x plus y minus 4 is equal to 0. And we need to find the area of this region R. So what would help us is if we were to graph this and see what the region roughly looks like. So here we have something like this. Y equals x squared roughly looks like this. X squared over 2, sorry. And x plus y minus 4 is equal to 0. That would mean y is equal to 4 minus x. So that's 4 roughly right here, and x roughly looking something like this. And the region R would be right here, where I'm shading this area right here. This is what we are asked to evaluate. Okay, so let's, the first thing I want to do is find the intersection points of these two graphs. So we have x squared divided by 2 is equal to 4 minus x. X squared equals 8 minus 2x. X squared plus 2x minus 8 equals 0. And you would get that x equals negative 4 and 2. So the intersection points are negative 4 and 8, negative 4, 8, and 2, 2. 2, x equals 2, and x equals negative 4. This is our area of integration. So this region R is equal to, so we have here y equals x squared over 2, and this one is y equals 4 minus x. The line y equals 4 minus x is clearly above the graph x squared divided by 2, so we have here from negative 4 to 2. 4 minus x subtracted by x squared over 2 dx. This is equal to, let's just find the antiderivative now. So This is equal to, so it's 4x minus 1 over 2x squared minus 1 over 6x cubed from negative 4 to 2 is equal to over 3. This is equal to 18, and that's our answer. Alright, well, that concludes the lesson of the fundamental theorem of calculus. I provided you with 4 practice problems. I don't give the solutions to these. I only provided the final solutions to these 4 questions. Try to solve these yourself. Let me know if you have any trouble getting to the final solution in the comments, or just letting me know. So yeah, that's it. See you guys next time.